Welcome to 5.1, Solve Systems of Equations by Graphing. And we have only one objective, which is to determine whether an ordered pair is a solution of a system of equations. Okay, what is the solution and what is the system? First, let's understand system. Solution we've seen, so that's not a new thing. Systems of linear equations, when we use that language, when we say system, it means two or more linear equations grouped together. Okay, so together they form a system. So we consider two equations simultaneously. For the scope of our course, we're only looking at two equations together. You could have multiple equations, 3, 4, 5, and all that, but we're going to look at two of them. Okay, so you can imagine two equations that are grouped together as simultaneous equations. And so each equation is a line. Now you have two of them in one system. So you can imagine two lines on the grid. Okay, that's the whole idea. And we want to find the solution to that. Okay, so I want to actually draw a little visual here for you. Let's say your one line went like this. Let's say another line went like this. Right? The possibility that these two lines meet is a very good one. The point where they meet, right? Point of intersection. The point where they meet is the only point that is common to both the blue and the red, isn't it? So that's the only one that's shared by both the lines. This implies that point is a solution to the system. Let's write that again. Is a solution to the system. Because I say system so that we understand that this is not just one line that we're talking about a common point for multiple lines, in this case, two lines. Okay. Can you think of another scenario leading to these two lines? How do you think they would work? Would they meet? We've already seen the scenario where they meet. Do you think they will meet again at another point? Do you think they could meet at 2 points? Or do you think they could never meet? Think about it. Okay. Well, I could draw two lines on the grid and they could appear like this. That was not the plan. Okay, yeah, this one. And let's say the other point went like this. How do they appear? They appear as parallel lines, right? So if they are parallel lines, where do they meet? They don't meet, they never meet. That's why they're parallel. Okay? They travel alongside, but they don't meet because the width between them is maintained, and so they never meet. So parallel lines will have no point of intersection. That means they will not have a solution. So parallel lines have no solution. Solution means something that's common to both, right? Even in real life, if you're finding a solution to a problem, it should appeal to both sides, right? If two people are having a problem and you're trying to find a solution, it should appeal to both of them. That's the same idea here. A solution should work for both. And in parallel lines, there is no solution. So we just declare that situation as no solution. And you probably didn't think about this. I use a different color. You probably didn't think about this scenario, but this also happens. Or probably you did. I will not underestimate you. You probably thought of this. Okay, you'll have to rewind a little bit because I can't do that trick. To see that I first had a blue line and then on top of it I had a red line, right? What does that mean? There is a possibility that these two lines can overlap, right? Just for us to kind of see the blue as well, I'm going to make it, it lined up so perfectly I didn't expect it. Look at that, see how well it lines up. I'm going to put it a little away So you could actually see both the lines. Okay. I can't believe I'm doing this. For once, I can't settle for perfect. Okay. We have the two lines coinciding. So we call it coincident lines. And here, what do you think is their point of intersection? It's crazy. Every point is a point of intersection. Okay? Every point is a point of intersection because they overlap, they are the same. If every point is a point of intersection, how many points are there then? Countless. Because every point, a line is made up of infinite number of points. And if we say every point, it means there are infinite number of solutions. You really can't count them. You simply have to throw up your hands and say, hey, everything is a solution. All real numbers are solutions. So there is really no way to segregate them. So these are the three possibilities when you have a system, right? A system of two equations, I mean. Imagine if there were three, then you have to see where all three meet and so on. Anyway, so these are the three possibilities when you throw two lines together in the same grid. And that's the system. Well, we kind of lost sight of the problem, so we'll come back to the problem. Determine whether the ordered pair is a solution to the system. And look how they've written the system. They're grouping the two equations together. So you have this large curly bracket that's kind of grouping them. Okay. So I have A and B. We have two parts to this question. We need to see if this is a solution or not. As you can see, in our first scenario, the point of intersection means the point is common to both the equations. Now we don't have a visual, we don't have a look at the graph, so we can't tell if they are, common to both. We only have a way of finding this algebraically. Well, we have seen previously, algebraically, both the lines must be satisfied by that same point. Meaning, when you plug in this point in the first equation, and when you plug in this point in the second equation, both of them must make the statement true. Okay, so I'm going to kind of create space here. Okay, so I'm going to divide this space into two parts because I have two equations, right? I'm going to answer part A, which is -2, -1. And I'll write the first equation on the left here and the second equation on the right here. Okay, so let's plug in for X and Y. I put the shells. I put a question mark. Remember, when we verify certain things, we really have no way to know if it's true or not until we have tested it. So do not declare them to be equal. Please put the question mark above it. Okay, X is -2 and Y is -1. Here also X is -2, Y is -1, right? Same point should be true for both the equations. So let's test them. Let's do them one by one. That's -2, and there's a negative and a negative, so combine them. Negative times -1 is +1. -2 plus 1 is -1 equals -1. Wow, that is a true statement. So that's great news. But we can't be too jubilant yet because we want it to be true also for the other one. Just being true for one of them is not going to work, right? That means it's only on one of the lines. The point is on one of the lines, not on both the lines. So let's come back here. 2 times -2 is -4. -1 times -1 is +1 equals -5. Okay, put a question mark. -4 plus 1 is -3. -3 equals -5. Is that a true statement? Oh no, sadly, that's not a true statement. So it was true for one, it was not true for the other, which means it's really not a solution to the system, right? It's a solution to one equation, but not to the system. So this implies -2, -1 is not a solution to the system. Okay, let's try our luck with the next point. What is it? -4, -3. I'll divide the page here as well. X minus y equals -1. And this side was 2x minus y equals -5. Shells for x and y, question mark above the equals. Let's plug in. X is -4, y is -3. Let's do the left side first. -4, negative times -3 is +3. -1 equals -1, just like before. Okay, that's good news. Come over here. That's a -8 plus 3, right? Negative times -3. And that's a -5 equals -5. Wow, that's wonderful because we got both of them working for that same point. So this implies -4, -3 is a solution to the system. That ends our section. I will see you in the next one. Bye.